Looking for twins of Earth? Maybe Tess can help. I'm Tonya Hall, and joining me is Dr. Sara Seager, professor at MIT and deputy science director of NASA mission Tess. Welcome, Dr. Seager.
Thanks for having me, Tonya.
So, what do you do at MIT? And tell us a little bit about your life journey that brought you to exoplanets.
Well, I'll start with what I do at MIT, but I do so many things. One of the main things I do right now is I help run an MIT-led NASA mission called Tess. It's like the girl's name Tess. It stands for Transiting Exoplanet Survey Satellite. And Tess is essentially 4 glorified telephoto lenses. They're only about 10 centimeters across. And these 4 lenses, they have like a giant baffle and a detector at the other end. And they look at the sky. These cameras together, they cover a huge amount of the sky, like as if 4, the constellation Orion? Imagine 4 of those side by side. That's the area it covers. And we're looking for planets orbiting stars other than the sun. We call them exoplanets.
And you had a really interesting journey to get you to working on this. Talk about like what brought you to exoplanets.
Well, initially it was just astronomy. Like when you look up at the night sky, I know not everyone can because the city lights and smog and everything. But if you ever get to go out somewhere clear where you can see all the stars, it is just fantastic. I always loved the stars. I always loved astronomy. And then when I got to high school, I took physics, which initially I didn't like. But after a while, I actually realized you can at least try to describe the world around you with an equation. And so I could bring those 2 things together for myself, like stars and equations that describe stars and galaxies and planets. And that's how I got into it.
We recently spoke with Dr. Angelos Tesaris of the University College London about finding water on a super Earth called K2-18b. Finding water on 18b was quite a surprise, wasn't it?
Okay, they did detect water vapor in this exoplanet atmosphere, and it is really awesome. We actually know of a lot of planets now, thousands and thousands of planets, and a small number of those we can study the atmospheres with the Hubble Space Telescope, and that's what the group did. They used data from the Hubble Space Telescope to show the planet had water in its atmosphere. And we know of a bunch of planets that have water, mostly hot planets, too hot for life, but it's definitely something out there.
The holy grail of planet hunting is finding a rocky planet with water, right? I mean, tell us a little bit more about Tess and how that tool is going to actually help.
Well, Tess is a planet finder basically, and its goal is to find essentially a catalog, like a phone book with addresses of all the best planets out there. And the goal is then later to use other telescopes which can study atmospheres, like Hubble. Hubble's not quite really good enough. There's a new Hubble, we call it a new Hubble. It's the James Webb Space Telescope. It's supposed to be launched in 2021. And we hope that that will be able to study the atmospheres of the test planets and find signs of water on them. It's kind of a complicated thing because the planet you were talking about earlier, I think it was called, I can't remember what it was called now. Do you, or the name of that planet?
K2-18b?
Yeah, K2-18b. It's not really a rocky planet, actually. It's massive and it's big, and so that's not quite there yet. So hopefully Tess or others will find a rocky planet, and hopefully the James Webb will find signs of water on it.
There was a lot involved in finding the right orbit for Tess that allowed it to stay in orbit without using thrusters. Can you summarize that story for us?
I can. And first, I want to tell you that most things we launch, like us here on Earth, communication satellites and other things, they're in what we call low Earth orbit. They're orbiting just a few hundred kilometers above Earth. And they actually, by doing that, they go through a day-night cycle, just like we do. But the day-night, it's quick. It's a 90-minute orbit. So you spend about 30 minutes in Earth's shadow where it's truly dark, and 60 minutes in Earth's daylight where it's not dark. Well, astronomers, we want darkness. And it turns out many orbits or around low Earth orbit, they're bad for astronomy because Earth is bright. It's like having daytime interrupt your night sky viewing. And Earth is hot. It's giving off heat, and it's really bad for astronomy. So the best orbits are very far from Earth. But Tess, having a somewhat limited budget, still had to orbit Earth. And so we used a brand new orbit. And I'll explain it to you. It's a 2-week orbit, and it's a highly inclined, highly elliptical orbit. So it's like very stretched out, like a giant ellipse. And it goes halfway out to the moon. And so Tess will orbit Earth in a 2-week orbit, and it's eccentric. So it goes out and slows down. Then it comes back if this is Earth, and it zips around quickly. And then it goes and slows down and then zips around quickly. Now, when it's out at the outermost part of the orbit, one time it goes around, the moon is on this side, like literally right Actually, I can't seem to do this right. The moon's on one side, then it orbits again, the moon's on the other side. It's in resonance with the moon. So Tess orbits twice every time the moon orbits Earth once. And the moon actually stabilizes the orbit. Because when Tess goes around, it's on one side, the next time it goes around, it's on the other side. And so it's kind of like tugging each way, keeping it just in the right orbit. And that's how we can keep that orbit. That orbit is kept stable by the moon for maybe up to decades.
What technologies
One thing I forgot to say, the beauty of that orbit is Tess is spending a lot of time away from Earth, away from Earth's daylight and away from all the other bad things Earth does for astronomy.
So then what type of technologies will be used to analyze the data that I'm sure it's going to collect, which is going to be interesting? How do we do that?
Well, with Tess, believe it or not, we're not using really too many new technologies. Like, we use computer codes. Some are kind of old school. Many of them are new, like with Python. We have many libraries in astronomy. We use Python. But essentially, like what we call photometry, measuring the brightness of stars from images, it has been done for decades to like 100 years in various one way or the other. Like in the old days, people used to literally use photographic plates. Today we use CCDs, charge coupled device detectors, or others similar to what you have in your phone, but way more sensitive, of course, and bigger. And in these detectors, they capture star images as a function of time. And we just literally use computers to count the brightnesses of each star as a function of time. And we're looking for a tiny drop in brightness that shows that a planet might be going in front of the star periodically. And so it's mostly like a series of computer codes. And it's humans as well. When the codes are done and spit out a bunch of interesting things, humans have to review it all.
What discoveries has Tess revealed to us so far?
It's operating for about a year and a couple months. And Tess has found well over 1,000 planet candidates. We found a few dozen what we call confirmed planets, and it's found some really interesting objects, actually. The most interesting ones, let me think of how to explain this, because it's just found so many interesting types of planets that we're trying to study more. One of the things it's found was multiple planet systems, like our solar system. You know, we have Mercury, Venus, Earth, Mars, but a lot of the planets out there, they're nothing like the planets in our solar system. One of the ones Tess found is 3 what we call mini Neptunes. It's a planet of twice the size, between 2 to 3 times the size of Earth, for which we have no planet like that in our own solar system. And by finding like 3, we call them mini Neptunes, because they're smaller than Neptune, but bigger than Earth. It's not very original, but by finding 3 of those in the same system, we hope to be able to follow those up with the Hubble Space Telescope and see, are they all the same? Are they all different? What are they made of? That's one of the interesting discoveries.
Just a little scary, that's all. So Tess's mission was to extend through 2022. What do you expect to accomplish with the extension?
Well, we expect to just find more planets, really. The planet is periodic, so every time it orbits the star, if it's aligned just so we can see the planet go in front of the star, we get another drop in brightness. And we actually stack the transits together to build our signal. So we hope we can find smaller and smaller planets by extending the mission and to cover more and more parts of the sky.
Explain how Tess will support the broader astronomical community through the guest investigator program.
Well, first of all, before we even get to that, Tess has no proprietary time. That's like, imagine if you invented a brand new product and you weren't allowed to make a patent on it. Everyone can just use it and sell it and do stuff with it. So it's a NASA rule, so anyone can look at Tess data. We have an archive, it's called MAST, M-A-S-T, MAST, it's the official astronomy archive. There's exopop Tess, there's lots of ways you even, if you wanted, could download the data. As soon as it's been analyzed, it's available to the public. So the entire astronomical community can use it. As you mentioned, black holes, people look for asteroids, we found a comet, people find supernova, like there's tons and tons of stuff in that data that literally anyone can use. The GI program, it's called Guest Investigator Program. So let's say you had a good idea and you wanted to get money to do that idea, that's you'd propose there. The other thing is that, you know how data rates, like how much data you get on your phone and stuff, it's always a problem. Like, do you ever try to load something on your phone, it's so slow and you're like, oh, I need more speed. Well, going from a spacecraft to Earth it's even slower. We get even less information than we want. So we cannot send all of Tess data down to Earth. And what happens is we can send like a full frame image, our whole image down. we have to bin the data on board to every 30 minutes. And then some special stars get to be at 2-minute cadence. So some, pre-chosen set of stars are like special, and those we can send more data down for. So if you propose to the GI program, you can also say, hey, my object is worthy of getting 2-minute cadence. It's special. It should be in the category where we get more data for it. So those are the two things you could get out of the guest investigator program.
Well, the work you're doing is very interesting. And thanks for joining us to shed some light on it. Dr. Sara Seager, professor at MIT and deputy science director of the NASA mission Tess. If somebody wants to connect with you, Sara, what's the best way they can do that?
Well, they can find me on Twitter at Prof. Sara Seager. They can look at my website, saraseager.com. And I'm also on Facebook if they just search my name.
There you go. All over social media. And if you guys want to find me, you can do that right here or go to tonyahall.net. Thanks for watching.